All right. Challenges facing renewable energy resources. So renewables are things that replenish on very short timescales. Like the sun replenishes itself every nanosecond. Wind is replenished every couple of hours. Hydro is replenished every couple of days. So these are short timescales. So they will not be depleted. Within a year. They won't be depleted within a lifetime. Alternatives are energy resources that are substituted for primary energy resources today. So primary energy resource is the stuff that runs society. So oil, coal, gas, and alternatives would be something like tar sands. It's not oil, it's tar that then gets distilled and turned into synthetic crude oil. So that would be an alternative. Renewables are better than alternatives. Alternatives are a euphemism that big power energy resource companies use to say that they're not actually doing fossil fuels. Okay, so I said I got all this from David Fridley's paper, 9 Challenges of Alternative Energy. I put a link to it here on the lecture so you can check it out on your own. Further information and thinking along these challenges is from De Rosa. He's a prof down at Stanford, Fundamentals of Renewable Energy Processes. And yeah, I want to give credit where credit's due. A lot of these slides come from Fridley's paper, so don't sue me. So challenge 1, scalability and timing. When someone has a new idea, there's usually a lot of excitement surrounding it if it's a good idea. And this can be anything, a technology, an energy resource, a computer app, a business venture. People are like, oh, we should do this. We should work. We should figure out how to make this happen. And sometimes if it's a energy technology, there'll be government funding. If it's just a business idea that you and your friends are coming up with, the funding comes from yourself, or if you're lucky, from your parents or something. And so there's this initial excitement, an initial wave of funding, but then things get hard, right? You run into challenges and it becomes difficult to sell the idea or to build enough of them to bring them to market. So this is this prototype or demonstration phase. And this is where you need additional funding to make things happen. This can come from entrepreneurs and seed or angel investors in the energy space. If that doesn't happen, then the idea just dies. Then the next phase is this commercialization phase. So you need things like early adopters, people that are maybe not as worried about getting a total return on their investment, but they think the technology is interesting or exciting and will lead to promise later on. And so these are the people that bought Teslas back in 2008 or something. And the technology or idea can often die here because of the difficulty of scaling things up, building enough of them. There's some really cool battery technology that requires a technique called vapor deposition, where atoms are laid onto the battery cell at one layer at a time. That's a very time-consuming process. And so even though these batteries are really amazing, they're not at scale yet because we haven't developed a machine to build that well. Yeah, we need the machines to build the machines to build the machines to build the thing. Finally, if it's successful and early adopters come along and secondary adopters come along and it becomes a technology or an application that makes life better or makes things less expensive, then it'll really take off and it'll enter the market and become ubiquitous. And that's what we're seeing starting to happen with electric vehicles, and we'll see that in the next 10 years. But most things die right here. Most ideas don't get past here without extra help. So that's a big challenge with renewable energy technologies and resources right now. The other issue associated with scalability and timing is just replacing this massive infrastructure that's in place. So this chart I've shown in, I think, lecture 7 or something on energy quality. And this shows energy transitions at a US scale, but really this could be mapped to all of global society. And we were all burning wood for time immemorial until the advent of the Industrial Revolution and using coal and steam engines. And so that happened. in the 1700s, but coal did not begin to dominate until a couple hundred years later in 1900. And then it took another 70 years for coal to be replaced by petroleum. And right now, petroleum is being replaced by natural gas. A little bit of nukes, but that's now become prohibitively expensive. Nobody wants to insure a nuke plant. And so now we're starting to switch to renewables, but we're still actually in the transition from oil to gas. We're not going from gas to renewables yet. And so we really need policy and market incentives to drive this change more quickly. These sort of organic transitions take time, and they're only there out of convenience. And so we need to use, our frontal lobe and think about the future and drive this transition more forcefully, again, with policy action. All right, so this is just saying the same thing again, looking at a few different technology, or comparing energy transitions to technology transitions. So energy is what makes the technology work. Technology is the utilization of an energy resource. And so technology transitions actually happen much more rapidly than energy technologies. We find new and better, clever, faster, less expensive ways to use the energy resource. So here's, coal taking over from wood, took about 66 years, oil taking over from coal, 52 years. And I don't know what I think I've typed 35 years. That's what I meant to type, not 135 years. Anyways, technology transitions really rapid. So as soon as the Model T started coming off the assembly line, they took over from horses in only 12 years. Diesel taking over steam trains only took 12 to 16 years. And then, using different ways to make steel, to strip, to purify iron, to make steel, really fast transitions. So technologies can happen pretty quickly, but the energy underneath the technology happens slowly. So that's another challenge. Challenge 2 is commercialization. Again, you can have a great idea, you can prove it in a laboratory, it can be successful, but it can take a long time for it to actually become commercialized. And so, heat pumps have been around since the 2000s at commercial scale, but still people are burning natural gas in their homes just because their boiler works or their furnace works, and it's going to cost money to replace it, even though that they would, save money by switching to an electric heat pump and save a lot of carbon, save a lot of energy. And so this adoption of new, better technologies can take a long time with commercialization. Anybody know when the lithium ion battery was invented? Not like the exact date, but like the decade they were invented in?
60s, 70s?
70s, but they didn't become widespread till the 2000s, till yachts. That's just because it took a long time to build the machines that build the batteries to scale them up to commercial scale. And so these transitions with different energy technologies, they can happen quickly, but to actually spread them out throughout the world takes time. And that's a problem for investment, right? Because investors, they want a quick return on their investment. They want to start making returns within a year, if not sooner. And so the investment into new energy technologies is pretty poor when you compare it to IT, information technology, in particular apps, right? So if I'm a VC living in Palo Alto and I got my office on Sand Hill Road and I have $10 million burning a hole in my pocket, I'll pay like 4 nerds to make a new video game on an iPhone rather than invest in a new battery technology, because I'll probably I'll start getting return within a couple months on that investment versus these energy technologies. Energy, it's a much larger system. It requires all sorts of distribution. It requires actual physical things. It's not just an idea or some computer code that can be downloaded. And so it takes a long time, and it requires much more capital investment. And investment firms are going to look for quick returns rather than these long long time scale returns, even though they may end up paying out more in the long run. All right. What were they before lithium? Just simple acid cells like lead acid cells or nickel cells. There were some other flavors like metal hydroxide and nickel cadmium and things like that, but they tended to have pretty short cycle life. Like they didn't last too many charges and recharges, and they were pretty fragile. Like if you discharge them too far, then they'll create secondary chemical reactions and break and no longer work anymore. All right, good question. Yeah, feel free to interrupt in any of this or share your own ideas. Challenge number 3, substitutability. I have a picture here of a gas pump and a Tesla supercharger. Anybody know how many superchargers are between here and Seattle? Not that many. Good dress. There's one supercharger station. It's at Bob's Burgers and Brews in Mount Vernon, I think, Burlington. And I don't know how many actual like chargers are at that location, but not that many. The point of this slide is how many gas pumps are between here and Seattle. Oh, so Thorough, I keep seeing tons in shopping areas. Yeah, you're seeing electric car ports. They're very different in terms of their power delivery. Electric car charging ports at a grocery store maybe are like 5,000 watts, but the superchargers can like spit out like 25,000 watts. So you can have a burger and a beer and your Tesla will be charged. Whereas at a store parking lot, you'll have to keep it there overnight. Yeah, we even have 6 charging spots up at Western. A student of mine helped initiate through the Sustainability, Equity, and Justice Fund. So if you have a cool idea like that, let me know and we can draft a proposal and get some money and do something like that. So how many gas pumps between here and Seattle? More than the number of electric charging ports? Thousands? Yeah, probably something like thousands. So it's going to take a while to change infrastructure. This stuff already exists. It's been slowly built up over the last 100 years, and to swap them all out for charging stations is going to take a while. And not to mention cleaning these things up. Anytime you have these gas stations, there's a big tank underground that needs remediation. So substitutability, switching from one energy technology to another can take time, especially when there's huge infrastructure already in place. The other substitution issue with renewables is they can't be on all the time, like many fossil fuel power plants. Now, fossil fuel power plants, they can't be on all the time. You still need to maintain them and bring them down every once in a while. But like a coal thermal power plant can be operating 70 to 90% of the year. Natural gas combined cycle 60% of the year. So nuclear power can pretty much run flat out all year long. Same with hydro, but these photovoltaics and wind, they're only available 12% of the year to about 40% of the year. And so you need to build many more wind turbines of a specific capacity to swap out for like a nuclear power plant or a coal-fired power plant. So it's just another challenge with substitutability. Challenge number 4 is material input requirements. A lot of these renewable energy technologies require materials that are rare in the Earth's crust. Lithium-ion batteries, the long cycle life, safe lithium-ion batteries require cobalt. The new NMC cells don't require nearly as much cobalt, and that's the one that Tesla's working on, so that's exciting. Wind turbines need very powerful rare earth magnets, so neodymium. This stuff isn't just like iron that we used to need when we were running things off oil and coal. And so these more rare materials will make the spin up of renewables a challenge as well. And I hope you're not getting bummed out by this lecture. Each one of these challenges is actually like a real opportunity to, discover something, make the world better, make a ton of money. So when you're seeing each one of these challenges, you shouldn't give up. You should try to identify a solution, because you'll be rich if you do. Here's a bunch of different rare materials. This table is really interesting. So it's saying the fraction of today's total world production. So let's start with this first line, gallium. 28% of all gallium today, or at least in 2006, it's going to be more now, went to making thin layer photovoltaics, integrated circuits, and LEDs. These are all very efficient energy technologies. One generates energy, the other ones use energy. By 2030, it's speculated that we will need to increase production by 6 times 3 by 1,800%. That's a big ask. So we need new mines, we need new mining equipment, we need new distribution, more factories to refine the gallium. And so these will be bottlenecks unless we're able to figure this out. Same with neodymium, increased 600%, 700%-ish, all these other things. So yeah, neodymium is for permanent magnets and wind turbines. There's all sorts of stuff. So cobalt, we'll have to double production by 2030. This is probably wrong, actually, because the EVs have taken off so much in the last 10 years from 2010 to 2020. I'm guessing this is much higher number now. But you get the point, right? These are rare earth materials. They're not present in abundance within the crust of the earth. And so we'll need more mining, more extraction. And some of the locations where we find the greatest abundance of these rare earths are old continental crustal areas. And so Alaska actually shows a lot of promise. And so there's a lot of resource exploration by geologists happening there. But other locations include Western China and Afghanistan. Afghanistan obviously is a geopolitically destabilized region, and acquiring those resources there for world use might not happen anytime soon. Jonah said, wait, what? Just talking about rare earths, where to find them, and that we'll need a lot more for the renewable transition. It's a paper I wrote back in 2013. I was looking at how much energy we could store if we use the critical chemical required for that flavor of energy storage. And so this chart here shows energy storage potential in gigawatt hours. For comparison, average daily world electricity demand is here, this line. And SPR is the Strategic Petroleum Reserve. So the United States has a bunch of oil they keep underground in places like Alabama, Louisiana, and Texas, such that if the world goes to war, we can operate our military for at least 90 days. So this amount of energy storage is an order of magnitude greater than total world electricity energy demand, and far greater than the amount of energy storage that we could manufacture if we took all the lithium, all the cobalt, mined in an entire year to build batteries out of it. So to satisfy, to be able to store enough to satisfy world electricity demand, we need to grow our annual production of these materials 1, 2, 3 orders of magnitude. Now, we wouldn't have to ever store that much, but you get the idea. If we were reaching some techno utopia where we have solar panels and wind turbines all across the globe and enough batteries everywhere to store that energy all the time, then we're going to have to extract far, far, far more resources. Something like sodium sulfur actually shows a lot of promise, just because sodium and sulfur are very abundant elements in the crust. But these batteries aren't as good as lithium ion batteries. Their efficiency is like 70% versus 90%. But Japan's big on sodium sulfur batteries. Similar chart. This is showing materials for energy storage. And what we're seeing here is mass fraction within the lithosphere. So this means 10% of the crust here is aluminum, whereas, 100,000th of the crust is something like lead or lithium. And so these, as elements become more and more rare, their fraction in the crust becomes lower and lower. The annual production also gets lower and lower. If something's really abundant like iron, then we produce a lot of it. And so these things that we need, like vanadium and lithium and zinc and cobalt, will require much more mining operations to generate enough. Unless someone discovers an awesome new technique to extract lithium out of seawater, then we'll have it made. And then obviously, like, stuff that there's a lot of doesn't cost as much money. Stuff that's rare costs more money. That's just supply and demand market economics. What about non-chemical batteries? Yeah, so this right here is pumped hydro storage. Some people call it pumped storage hydro. This is just pushing water uphill. The only thing you really need is calcium for cement and iron. And so this shows tremendous promise for storage. Anywhere you have a continental margin near the ocean, you could use the ocean as the lower reservoir. Hanging valleys along rivers, like in the Columbia, you could use the river as the lower reservoir and a hanging valley as the upper reservoir for pumped storage. 99% of storage today on the grid is pumped storage. There's 6 gigawatt hour storage in Virginia, another massive one in, maybe I got that wrong. I know it can generate 6 gigawatts. I don't know what its storage capacity is. There's another massive one in Scotland and another huge one in Wales. So yeah, geologic storage technologies, non-chemical storage technologies would be able to satisfy this demand pretty quickly. They just require conducive geologies. You don't have a hanging river in Manhattan, for example. And that's why these chemical storage technologies are exciting, because you can put them anywhere. All right, challenge number 5 is intermittency. Wind's not always blowing, the sun's not always shining. I've shown this chart before. This is 30 days of solar insolation in gold, wind in blue, and power demand for Portland, Oregon in red. And supply does not correlate with demand. And so you need a flexible energy strategy or flexible grid strategy. So you need something like a natural gas peaker plant or a battery or deferrable loads. That means being able to have smart devices in your homes or businesses that only operate when times of excess renewable generation, for example. So you could tell your dryer, I want my clothes dry by tomorrow morning. I don't care when you dry them. And then the dryer would get some signal that says, okay, there's a lot of wind on the grid right now at 1:13 in the morning. I'm going to turn the dryer on. So here's some of these flexible generation pathways to satisfy that challenge of intermittency. So we can store renewables. We can just store power directly from the grid, or we can have responsive gas generation. That's what we do today. I don't have flexible energy strategies like deferrable loads and smart appliances on this chart, but it should be there as well. Okay, challenge number 6, energy density. Not supposed to use the word magic as a scientist, but gasoline is magic. Just there's so much energy that we can store. You'd have, well, not a demitasse, but a cup of gasoline can take you and 4 friends 5 miles down the road. It's ridiculous. The gas tank in a Honda Civic is this big and it goes 300 miles. The battery in a Tesla 3 is the entire bottom of the car, the whole base of the vehicle, and it takes you 300 miles. So the energy density difference between gasoline compared to a lithium ion battery is like 2 orders of magnitude. And that makes a really big difference. And it's really challenging, not only for having enough energy available to do what you want to do, like drive to Seattle and back, but also in terms of shipping that energy around, transporting that energy. It's really easy to deliver gasoline or diesel anywhere you want to. And that's one of the big challenges in like military applications, right? The military is very interested in reducing its oil consumptions for geopolitical reasons and strategy reasons. But if you're at the tip of the sphere, in some valley in Afghanistan, you're going to be carrying drums of diesel with you, not lithium-ion batteries and solar panels. It's just going to be lighter and more reliable and effective at this stage. I saw something about Thor wrote, I saw something about the 1,000,000-mile battery from Tesla. How is that so much better than normal batteries? I don't know. Maybe they're talking about integrated over many cycles. It's probably what it is. I'll have to look that up. Thanks for bringing that to my attention. Some of the batteries that can store much larger would be this theoretical like thermodynamic limit on a lithium-ion battery. So that's if all the chemical reactions were perfectly reversible and didn't produce any entropy. The zinc oxide theoretical limit. So this is an interesting battery because you're one half of the battery is just the air, and they're working on sulfur air batteries, lithium air batteries, and that would cut the weight of the battery in half because you only need half a battery and double the energy density. So there's some exciting things coming down the line, but we're just not there yet. Big opportunity. If you have the aptitude and the interest, then getting a degree in material science would be a wise pursuit at this stage. Oh, ethanol, about half the energy density is gasoline, and that's why if you fill your car with no ethanol gasoline, like that gas station down in Fairhaven, you can get no ethanol gasoline, then your car will go farther because it has more energy in the tank. And when you see that sign at the gas pump that says this fuel may contain up to 10% ethanol, it contains exactly 10% ethanol because it's cheaper than gasoline, and they're gonna sell you the cheap stuff. Challenge number 7, water use. So this is specifically for fuel alternatives, so-called renewable fuels from biofuels and things like that. And to grow plants to make fuel requires water. And so this is the gallons of water required per gallon of fuel output. Gasoline, you need a little bit of water, especially if you're down in Kern River Valley near Bakersfield and you have enhanced oil recovery with steam, for example. But in general, gasoline production doesn't require any water. But when you're growing food to make fuel, you need water. So the least intensive one apparently is a sugar beet. Much more intensive plants. Well, you can read it as well as I can. So corn requires like 2,500 gallons of water to make 1 gallon of ethanol. And this is starting to enter in this scary hate triangle that this will be present throughout this century, where you have water and food and energy all kind of competing, and that's not ideal, right? Biodiesel takes even more water. I don't know why. I'm not a botanist. Challenge number 8, receding horizons. So there's 2 things to talk about in this one. The first one may be a little easier to grasp, and that's just elastic supply and demand economic forces. If myself and everybody in my neighborhood and then everybody in Bellingham all switches off natural gas, we're not going to be paying any more money to Cascade Natural Gas Company. The price of natural gas that they sell may actually go down because the demand for it isn't there. And so then all of a sudden natural gas will look attractive again compared to some other technologies. If everybody switches to electric cars, then gasoline prices, oil prices may be driven down. We're definitely seeing that with the coronavirus. Oil prices tanked. And so now all of a sudden, gas is at $2.50 or less, and the economics of switching to an electric vehicle aren't as attractive as they were a year ago. Melvin writes, isn't that the point? Yes, but it makes the switch harder and harder if the fossil fuels get cheaper and cheaper. Another receding horizon is the so-called Jevons paradox, and he was an economist in England, I think like 150 years ago or something. I don't remember exactly. This would be a good podcast topic, so I could actually learn something. And he realized that as the efficiency of pumps that pumped water out of coal mines increased, they were able to just dig more and more coal out of the ground. And so even though their pumps were burning less coal, the actual consumption of coal went up and up and up and up just for the pumps, because now the pumps could access more coal and they were running more often. And so this Jevons paradox thing has been seen with Prius owners in the last decade. People with a Prius, all of a sudden now they can go 40 miles per gallon instead of 20 miles per gallon. And they were actually increasing their travel. And so as efficiency increases, energy consumption goes up, sometimes so perversely that the energy consumption is greater than it was before the efficiency increase. You can see this with any homeowner, your parents, for example. I'm distracted. There's a yellow jacket in my house, but it's not a murder hornet, so I'll just let it ride. Must have came in on some firewood. So you stay over there. Any homeowner, they may buy a second fridge because they're really efficient now. In Joel's lecture on Friday, he was talking about the gain of efficiency of fridges. But what happens to their old fridge? It just goes in their garage, right? And it gets filled with beer. And so now they're using more energy than they were before, because they're using the same amount of energy they're using with their old fridge. And now they have a second fridge that's using energy. So as energy efficiency increases, it can drive costs down, and then people have more money to buy more stuff that uses energy. Now, this isn't a hard and fast law. It does break in many instances. So the classic example Jevons paradox breaks is in lighting. LED light bulbs are 10 to 20 to 30 times more efficient than an incandescent light bulb. And I swap out all my lights with LEDs, and I didn't decide to buy. So there's six little lamps in that, 6 little lights in that lamp up there. I still have 6 lamps. And so I've reduced my energy consumption by a factor of 10. I didn't buy 60 LED light bulbs and put them all over my ceiling. So there are many cases, as long as the energy service is completely satisfied with a much more efficient technology, then Jevons paradox doesn't hold true. But if there's still a desire, a need, or want for that energy service, then Jevons paradox can happen, is the case with like a Prius. No matter what, energy efficiency is a great thing to do, but it can create these little pathological results. Challenge number 9, net energy analysis. I already did that lecture on net energy analysis, but it takes energy to make energy. It takes energy to mine these resources, build these machines, deliver the electricity, etc. Here's the energy return on energy invested in energy equivalents or electricity equivalents rather than primary energy. That's what that E stands for. It doesn't matter. Natural gas has an EROI E of about 14. This has gone up recently due to Marcellus shale and hydrofracking. PV has an EROE of about 12. This has gone up because the technology is getting better. Wind has an energy return on energy invested of 85, 86. So what does this mean? It means that if I spend energy building a wind turbine, I get 86 units of energy back. That's a great investment, and I can use that energy to do all sorts of extra things. So you may initially look at this and say, oh, PV looks about parity at gas. That's no problem. Wind's way better. So net energy analysis will not be a problem with renewables. But recall that they're intermittent, so we have to firm them up somehow. And if we firm renewable resources with energy storage, now we have to spend a lot more energy building these storage devices, operating these storage devices, which aren't perfectly efficient. So we lose some energy along the way. and now their ERI is reduced sharply. So taking something like wind, and then, so these colors represent different resources: wind, PV, grid, and gas. And then the y-axis is just energy return on energy invested. And then the x-axis is different storage technologies or gas generation technologies. So if you take something like wind and crank it through a lithium-ion battery, your EROI goes down from 86 or so all the way down to 21. If you put it through something like a lead acid battery, which would be crazy, then now we're below natural gas. So it's still a pretty good picture for wind. But if we compare that to PV, which had a starting EROI of about 12, you run it through a storage technology, and now it's getting a net energy return that's less than natural gas. I'm personally fine with this trade. I would rather trade energy for carbon at this stage because we have plenty of energy and way too much carbon. So let's reduce our carbon footprint. Tony asked in class or in chat, what about pumped hydro? Yeah, so these two geologic storage technologies, pumped hydro storage and compressed air energy storage, are the best in terms of their net energy return. And that's because they can be built at massive scale, get a tremendous amount of cycle life, meaning you can charge and discharge them over and over again. And they're made out of really simple materials. Both pumped hydro storage and compressed air energy storage is you take like a depleted gas reservoir or oil reservoir. Usually it's in a salt dome. It's just a big hollow bubble of salt underground in Alabama. And you can fill that up with air at up to like 90 bars of pressure and then run a turbine with that air. And so, yeah, both these technologies are made out of holes in the ground, which is a pretty basic technology. And so it doesn't take a lot of energy to build them. And so they have really great net energy returns when coupled with wind. Or even the power grid, it basically becomes at parity with natural gas. Problem again with these geologic storage technologies is they're not available everywhere. So that's just another challenge. But again, it's at least the carbon is much lower with these technologies, unless you're storing grid energy. That's not the best. All right. Wow, I'm done 10 minutes early. Any questions, thoughts, ideas?
There were orcas in the bay today.
That's awesome. Where?
I could see them from Mathis Hall. So they were, they swam towards one of the marinas, and a boat was kind of following them. And yeah.
Cool. Thanks for sharing. That's really cool.
Yeah.
I had a question about recording our podcasts.
Yeah.
I thought you might have mentioned something about that, but I'm not sure.
Yeah. In case anybody came a teeny bit late, Wednesday will be a podcast recording day. So there will be no lecture. I'll still hop on Zoom in case people have questions about things or people forgot about this announcement. But you're welcome to just get together with your group on whatever, internet communication service you so choose. Don't leave anybody out. And that's a dedicated time that you'll have to record your podcasts. And hopefully it's a time you can all get together because it's normally a time that you'd be in lecture. So Wednesday is podcast recording. Friday, maybe a short lecture, maybe just a study session, help for the final homework. And then Monday we'll have a fun lecture about what to do next with this whole energy climate crisis. Ian wrote, you said we don't all have to be on the recording, correct? Yeah, you don't all have to be on the recording. Just make sure that, everybody did their fair share of work with the project. Katie, sorry to cut you off. You had a question?
Okay. So are you going to ask us these questions of like, what are the 7 challenges of finding efficient energy? Like, will that be on the exam or?
In the final, I'll probably have something like identify 3 challenges to renewable energy resources and provide a solution. Something like, I'll want 12 sentences.
Okay, then I'll know what to study.
Yeah.
And we'll kind of be getting those ideas from your lectures, right?
Yeah, I mean, you can either click that link to David Fridley's article, or you can just watch this lecture again on YouTube. I posted all the last 3 lectures on YouTube. Finally, the election and stuff, I kind of stopped trying at life. I'm happy with the results, but it's very distracting. Yeah, so recording day Wednesday, study session Friday, fun lecture next Monday, and then Thanksgiving break.
Bye.
All right. I'll hang out for another 3 minutes in case people have questions. Otherwise, you're free to go about your day.
Awesome. Thank you, Charlie.
Yep.
All right.
Thank you, Charlie.
I have some questions not regarding lecture or anything.
Yeah.
Well, I do have a question regarding last lecture when you had the guest speaker on Friday.
Yeah, Joel.
Yeah. So I am an energy minor. This is my minor. I'm a chemistry major, actually.
Awesome.
Yeah. So I am trying to register for class. This is like, I'm starting my minor right now because I'm in second phase of chemistry. So what's the next class? Like, we do have that PowerPoint that he was presenting on Friday by any chance, somewhere up in Canvas?
Yeah, I don't have his slides, but let's check out the Institute for Energy Study website.
Okay. Yeah, because like I'm trying to do a what's it called? I'm trying to pick my classes. This is the first one in this series, and then I'm trying to figure out which is the next one after this.
Yeah, and you want the science minor or the BA or the policy minor? Which one?
I think the policy minor because I'm already a science major. So.
Okay, great. Let me share this. So here is, I just typed in WWIES into Google, or you could type in Institute for Energy Studies. That's what IES stands for. And it comes to this page. So you can click programs, and then here's minors. So let's click energy policy.
Well, what was it? IEU? Wait.
IES, Institute for Energy Studies.
Oh, okay,
Yes.
I see.
Yeah, WWIES.
Okay.
Yeah, so then if you click programs, which is at the top here,
Mhm.
and then here's your different degrees. So you could click energy policy.
Okay, there it is.
So energy 380 would be the natural one, but it's very similar to energy 101, just with more of an environmental focus. And so you've already taken energy 101, so you wouldn't take this one. They kind of sub for each other. Energy 350, if Christine Grant is teaching that next quarter, you should totally take that. She's our new Whatcom County Public Utility Commissioner.
Oh, okay.
She's doing a lot of really good things.
Yeah, a lot of these classes kind of like they're at the same time as my chemistry classes, so it's kind of hard to take. That was the issue with 380. So I'm trying to like, and also with the science minor, energy science minor, is it like the same thing? Because would we have to take like physics, math, all those prerequisites? Because like I pretty much already taken all that.
Yeah, the main difference between policy and the science minor, the policy minor is just gonna have more economics courses. The science minor is gonna have like Tim. Do you know Tim Kowalczyk? He's a professor in chemistry.
He's my advisor, actually. And I'm taking him right now for PCAM.
Awesome. Yeah, so he teaches some energy science classes where you learn, exactly how the photovoltaic works, exactly how batteries work, the actual like the equations that govern their operation. So that's what you take more on the energy science minor. Let me check that out. It's like, so 320 science of energy resources, 420 advanced energy science.
Okay.
And then you can take some like, building analysis. So these are the kind of classes that Joel teaches where you like design a net zero carbon building or something with a partner.
Okay. Yeah.
Yeah. So have a look at
Mhm.
Institute for Energy Studies here and these programs. You can have a look. And if you have questions, email me or totally email Gail Cowan. She's
Mhm.
amazing. Like she's like one of those rare people where like she's probably hundreds of people's favorite person.
Yeah.
Like it's like
Mhm.
a fairy godmother. So she's really good. She'll help you out.
Cool.
Yeah.
Thank you.
Yep. All right. I'm gonna peace out, y'all. Unless you have a question.
Oh, yes, please. So in my homework number 5, the postcard outline. So for some reason, it's from the group that I'm not supposed to be in. It's not my group. So do I need to resubmit the homework?
Oh, no. Let me check it out. Do you know the number of the group you're in?
Oh,
Uh,
okay.
send me an email with your group members, and I'll put you in the right group. I'll figure it out. Okay.
Okay. Can I just put it in the Zoom meeting?
Did someone from your group already submit the outline?
Pretty sure they did.
Okay, then you're probably okay. Just email me and let me know what group you're in. Please don't submit anything because I don't want it to overwrite the submission for the group you're not in.
Okay. Thank you.
Yeah, you don't have to email me the draft. Just email me like, the name of somebody else in your group, and I'll be able to find your group.
Okay, thank you.
Thank you. All right, have a good one.
Yeah.